Hi, we're group number 6 and we would like to present to you our results for our project within ME 231A. Our project is about obstacle avoidance for 2D quadrotor with hanging load. I'm Martin and we're going to present the first part of our presentation. So that is our presentation outline, which is also our project outline. So what we did in the beginning, we derived the model first for a quadrotor without load in 2D and then for a quadrotor with load. Then we generated a trajectory with a modified batch approach, which has obstacle avoidance constraints in it. And we'll talk about it later in more detail. And at the end, we tracked that trajectory with the MPC controller and compared that with a discrete time LQR controller and tested it on test cases. So motivation, why do we do that? Because quadrotors become more and more important in load transportation, and the conventional way of doing that is shown in the left picture. That's a drone of Amazon, and what they did is they just attached the package under the drone. The disadvantage of that is that the agility is influenced, and the dynamics is influenced dramatically by that. So what we did with our hanging load is to keep the agility of the drone by just letting the package hang on a rope. So what are the control design challenges of that system? So first, it is very underactuated. We have two number of inputs and 8 states. We'll go over it later in more detail when we derive the model. Then we also have nonlinear dynamics. We have input saturations. And we also want to include those obstacle avoidance constraints which are non-differentiable and non-convex constraints, but we used a way to reformulate them to be differentiable.
All right, hi, I'm Nathan Bucky. I'm going to be talking about the dynamic derivation for our system. First, we started with a simple 2D quadrotor for all of our test cases in order to ensure that our model was correct and that our algorithms worked. So the derivation for our model involves two thrust forces in the body frame of the quadrotor labeled F1 and F2. We have a 2D coordinate system with a z-axis in which gravity acts, and then a y-axis, which is just the horizontal direction. And then we labeled this F and M as the total thrust force and the total moment. So you can see the total thrust is just a sum of the two thrust forces from the quad, and then the moment is a difference of the thrust forces times the length of the arm length of the quad. So here our state variables are y, the horizontal position, z, the vertical position, and then the roll of the quad. Next, we added the hanging mass to the quad. So now we introduce these new state variable phi L, which refers to the angle of the mass with reference to the z-axis in the world frame, and then we include the same roll phi q, which is the roll of the quad with reference to the y-axis. And again, our input constraints are still F1 and F2. We do not actuate the hanging mass. So these are our equations of motion for the system. As you can see, they're highly nonlinear, so we had to do a lot of linearization in our control algorithms. The full state vector is 8-dimensional. You can see we define everything in terms of the y and z position of the load, because that's what we care about. We want to control the position of the load in the world, not necessarily the position of the quad. And again, our control inputs are still just F1 and F2, which we translate into a total force and a total moment.
Hi, I'm David. I'm going to talk about the obstacle avoidance trajectory generation we used. So we modeled our quadrotor as two polyhedra, which you can see on the right side in the picture. So the yellow polyhedron for the load and the cable, and the blue polyhedron encircling the quadcopter. So our control object is the union of those two polyhedra, and we're introducing M obstacles also as polyhedra, denoting them as O. So if we define our collision constraints by setting the distance between E and O greater than 0, we get non-convex and non-differentiable constraints, and then we reformulate them as dual constraints with dual variables to get smooth constraints, which we can use for standard nonlinear solvers as IP-opt. And then we use the batch approach to solve our path planning problem. So here are the 3 test cases we faced in our project. The first one is a keyhole problem, where the quadcopter tries to go from the top left corner to the top right corner. And the red line is the initial path we pass to the solver. The second test case doesn't contain obstacles, but it's a typical control problem related to the inverted pendulum. And the third test case considers 2 triangular obstacles and the path which is shown here. So I want to talk about a bit more in detail about our model we use for trajectory generation. As I already said, we introduced 2 new dual variables, lambda, which are related to the obstacles, and mu, which are related to the parts of the quadrotor, namely the 2 polyhedra. And then we define our cost function, which we minimize as a linear quadratic function of the time step, which effectively minimizes our final time, and a weighted sum over the control inputs. The first 2 lines of this problem formulation, they are the standard formulation for our batch approach, considering the nonlinear model, discretized linear input and state constraints. And the last 3 lines contain our dual obstacle avoidance constraints.
Hi, my name is Prashant. In the we calculated reference trajectories for three different test cases involving obstacles. In this section, we present the tracking controllers to track those reference trajectories. For our work, for the purpose of this project, we considered two controllers, LQR controller and MPC controller. In this slide, we present the infinite horizon LQR discrete time LQR controller. So the discrete time LQR controller involves linearizing the dynamics about the reference trajectory at each time step, and we use these linearized dynamics to calculate the feedback term and then use the feedback term to calculate our input to calculate the overall input of the LQR controller. As you can see, the feedback term is calculated by minimizing the cost function over the infinite horizon k is equal to 0 to infinity. So once the input is calculated, we use this input to simulate the dynamics using LQR controller. We use this LQR controller as a baseline for the MPC controller presented. So for the MPC controller used over here, it requires optimizing the problem at each time step over a horizon of n. So we chose an horizon of n as our horizon as 10 for our problem over here. And the MPC and the optimization problem involves minimizing the quadratic cost function between the errors in the states between the actual state and the reference state. And similarly, for actual inputs and the reference inputs, we use the quadratic cost function for our purpose over here. And the constraints involve dynamic constraints as shown over here. Once again, note that we use linearized dynamics about the reference trajectory. Hat over here represents the reference trajectory, and similarly bounds on the states and bounds on inputs are also various constraints used in the MPC. We solve this optimization at each time step and then use the input calculated at the time step to simulate our dynamics. Thus, we have our LQR controller and MPC controller. In the following slides, we present the various results between MPC and LQR controller.
Hi, my name is Ayush, and I'm going to be talking about some of the results for MPC and LQR tracking. In this slide, we show the MPC tracking controller for the keyhole problem, and you can see the simulation video on the left. On the right, we show plots for the MPC and LQR controller tracking. And for this problem, we see that the performances for LQR and MPC are very similar. And we'll come back to this point at a later slide. In this slide, we show the simulation results for the case with reduced input constraints. Namely here, the reduced input constraints are set to 30 newtons, whereas the nominal input constraints were set to 15 newtons in the trajectory optimization problem. On the left, we see the plots for the trajectories for MPC and LQR controllers, and we notice that the MPC controller has a much better tracking performance as compared to the LQR controller. And this is expected because the MPC controller takes into account the input saturations in its optimization problem. On the right, we see the plots for the two inputs, F1 and F2, and we see that the control inputs are within the input bounds for the MPC controller. So here are the tracking error plots for the first case with no input constraints and for the second case with reduced input constraints. On the left, we see that the performances are similar for LQR and MPC controllers, and this is expected because the input constraints are at the nominal values. On the right is the plot for the error with reduced input constraints, and we see that the MPC tracking error is much lower than the LQR tracking error. And again, this is expected because the MPC controller takes into account the input saturations in its optimization. In this slide, we show the simulation results for the two other test case scenarios. On the left, we have the swing up trajectory, where the controller is trying to get the load to the inverted position. And on the right, the controller is trying to avoid the two triangular obstacles. Both these simulation results are for the MPC controller. And we see that in both cases, the MPC controller tries to track the desired trajectory as closely as possible. So in conclusion, we developed a trajectory generation scheme for a highly nonlinear and underactuated system. We used results from a recent paper to reformulate our obstacle constraints to differentiable constraints, and we tested them on 3 different test scenarios. For the case where the input constraints were set to the nominal values, LQR and MPC had similar performances. But for the test case where we had reduced input constraints, the MPC controller performed much better than the LQR controller. And we showed trajectory tracking for both LQR and MPC controller in this project. Thank you.